application, they will give you the procedure to calculate QS for slender unstiffened elements. If you go to specification, chapter E7.2, they give you procedure for QA to calculate slender stiffened elements. So this is based on 13th edition. Of course, like I said, if you use 15th edition and newer, they have different method. But luckily, in chapter 5, or in 5th edition of your textbook, they have all of this example in calculation for Q for you, because 5th edition of the textbook still based on 13th edition of the manual. The general procedure for calculation of QA, which is the slender stiffened elements, is laid out as 2 steps. So you might have to write it down if you wish. Compute effective area of the cross sections. And this requires the knowledge of the stresses in effective area. So iteration is required. But the specification gives you a simplified assumption, so iteration can be avoided. So you got 2 choices. You can either use iteration, which will give you more accurate calculation and result, or you want to simplify your calculation by using assumption. Either way, I'm fine for your whole number 3 and midterm 2. Either way, I'm fine with that. You want to use simplify or iteration. So today, I'm going to go over both procedure for you, the calculation sample. So this will clarify your question about this procedure. Next, once you calculate effective area, you need to divide by the whole cross-section area, and this will give you the factor for QA. The QA again will be the reductions to account for slender, stiffened elements. So any questions or discussions so far before we show any example for calculation?
You should invest it. You have to become an investor and multiply your money. What number is that?
Okay.
Yeah, that's what investing is all about.
So now, let's look at one example. Example for before
Choose one. Choose a
in the
number.
textbook.
2000 what?
Determine the actual compressive strength of a HSS 8x4 by 1A with effective length 15 feet with respect to each principal axis.
Goes up and down, up and down.
Fy is 46 KSI. So, the first step to calculate is to consider the global flexural buckling strength. So, you need to calculate maximum slenderness ratio based on minimum radius of gyration. So this value you can check out from part 1 of the manual, and you will see the number is 1.71. Another value is Rx. The number is bigger than R1, so you use smaller value to get maximum slenderness ratio. So with that being calc, you got 105. Less than 200, that's the max. And the separation slenderness ratio between elastic and inelastic buckling global is 4.71. Square root of E over Fy is 118. So this is separation point. Because this actual, the real slenderness ratio is less than 118. So this is inelastic buckling. So you need to use AIC equation E3-2, you first need to calculate Fe, which is pi square E over K over R squared. You got 25.81 K psi. And then you plugging into this equation, which is E3-2. Then you got 21.82 K psi. So the nominal strength of this column for global buckling P nominal is the critical stresses you calculated times the gross sectional area, which is 2.70. And this number you need to also check out from part 1 of your manual. So with this being considered, you got 58.91 kips. So this is the nominal buckling strength for this column, global buckling.
But I mean, in your piggy
If
bank, it's
your
not even
column
gonna go up.
height is 15 feet.
So at least you're
So
trying.
any question up to these steps,
At least you make
any
some money.
questions
You're not
or
gonna become a
discussions
millionaire overnight,
or
but at
comments?
least it's going up. Instead of 100, you're gonna have 200. When you steady would have been just sitting there, not growing.
Hui, can you speak louder?
So this is for the local buckling nominal strength, right?
This is for global buckling. Mm-hmm.
Brad, you got a lot of money though. Go piggy, go.
Any other comments,
This
questions?
one not always full already.
No, sir.
Okay. Now, the next step, like I said, if you see the problems, is HSS. Most likely, you need to check the slenderness of local buckling for each element. So, from part 1 of the manual, you will get two values. One is H over T, another one is B over T. So, the HSS, let me briefly draw. It will look like this, because this is a rectangular shape, A by 4. A by 4 by 1/8. So, T is the thickness of the HSS. The H over T is the larger ratio. This is H. And then this is B. So this is smaller dimension and larger dimension for the elements. So you can think of these are 4 pieces of elements. So this is the first piece. These are larger elements, and this is shorter elements. And likewise, there's another one here, and there's another one here. So for HSS, like I said, all of these elements are Stephan elements. So in HSS, there is no un-Stephan elements. In HSS, they are all Stephan elements. Okay? So this you can check out from the manual, 66 and 31.5 for larger elements, and this is for shorter elements in the cross sections. Based on the AIC table B4.1 case 12, which is figure 4.9 in the book, in the textbook, the upper limit for non-slender elements for HSS is 1.4. Square root of E over Fy is 35.15. So in this case, your smaller dimension is less than this. So this is not slender elements, but this one is slender elements. So let me draw that picture once again for you. So for this HSS, these elements are slender, stiffened elements because this number is bigger than these limits. But for these two smaller elements in the cross sections, this number is less than 35.15. So these two I mark in green is not slender, stiffened elements. So local buckling will not occur in these places, but the local buckling will occur in these larger elements in the cross sections. Any questions or discussions?
Can you please help identify the H, T, and B again?
H over T is this dimension, H. This is H. T is the thickness. And B is from here to here. You are calculating the width thickness ratio for each element to determine if it's slender or not.
And we're gonna compare it with the formula.
The limits.
The limit, yes.
Mhm.
The limit. If it's going over, then it's gonna happen. The local buckling is gonna happen.
Yes. If you're more than the limits, you have local buckling. Then you need to consider Q factor for reductions of the strength. Any other comments?
Press play, baby.
No? Okay, so the larger dimension element in this case is slender. So the local buckling strength must be computed. Okay? Now, with that being said, because these cross-section elements, like I said, for HSS, are all stiffened elements. So your QS is 1. Because QS is for unstiffened elements. But in HSS, you do not have unstiffened elements. So QS is 1. You don't need to do anything for QS. But QA must be computed based on specification E7.2, which is E7.2B. This is based on 13th edition. Construction manual, page number 16.1-42. So, to calculate QA, you need to refer to this equation. So write it down if you don't have that equation. You need to satisfy this equation. B over T bigger or equal to 1.4 square root of E over lowercase f, where lowercase f is equal to Pn divided by AEFF, effective area, the reduced effective area. So, from here, there are two approaches, like I mentioned to you in the beginning of the class. You can either do iteration to figure out this f, or you can simplify the procedure by making assumption of this f value. So, let's starting from simplifying approach. Let's assume the f is equal to f1. So, from ASC equation 7-18, E7-18, the effective width of these slender elements is equal to this equation. B sub E is equal to 1.92 T square root of E divided by F times y minus 0.38 divided by B over T square root of E over F. But this number should be less or equal to the original length of the elements. But because this is reduced width, this is unreduced length of the element. And here, if you assume f equal to fy, then all this number here, you're just plugging into fy. So, the example for calculation this is the cross sections of that HSS 8x4. Okay, so you know that for the 8-inch side, which is from here to here, is 8-inch. Okay, so we are talking about this element. Okay, so we need to consider the original length. You need to reduce to some value. We call b sub e. It's not 8-inch anymore. It will be less than 8-inch after you consider all this calculation for b. So here, to use this formula, the t, you need to use so-called design thickness from the property table. So this thickness is not just 1/8. Remember, it's 1/8 times 0.3. So this is what we call design thickness. You can check out this number from part 1 of the manual as well. So this is nominal thickness when you call out HSS 8x4 by 1/8. But when you use this equation for t, the design thickness is this number 1/8 times 0.93. This number is by specification. This is not whatever theory, it's just by definition. You can come up with design thickness. This is how you got this number. F, you plug it into Fy. B over T, also from the manual. So you got BE is 4.784. So this is the reduced, we call effective width or effective length of this element. Likewise for this element, due to local buckling. Okay? Because our goal is to figure out reduced effective area. So we need to figure out effective width first, which is B sub E.
The security system is very sensitive. You don't want to be accidentally setting off the alarm. Let's carry on to the next room where we'll see the Statue
And then,
of Liberty. The Marquis de Lafayette was 19.
what is B?
Participated in the War of Independence. So young.
Okay, what is B? So let me go back,
He helped George
go to
Washington
next slide.
win the Battle of Yorktown.
What is B?
Everybody thinks it was owed to Lafayette's exceptional.
B,
I think it was also
you might think of
a miraculous. Natalie, you take care of Paris. I'll
this distance from here to here is how you call B, is 8-inch. But actually, it's not like that. For HSS, you need to pay attention. For HSS, during the manufacture process, this is not rectangular.
In exchange, you will bring me Lafayette's saber.
It will look like this.
Would you rather have an atomic bomb? No, I want
You will have a radius in the turning corner. So it will actually look like this when they do the manufacturing process for the HSS. So you'll see this radius at the turning corner in the each four, in each of the corner. Okay, so the actual width B that you measure for these elements is actually from the center of the radius of each turning corner, and the distance from here to here
Excuse me, sir, but
you got to remember is 1.5.
Superpowers should never be used for personal gain, only for the greater good.
Likewise, on the other side,
I wouldn't be able to open the safe because its key is in Paris.
from here to
inside
here,
the Eiffel Tower.
also 1.5 t. So your actual distance to measure for the B is from here to here. So it's 8 inches, the nominal length, minus 3t, 1.5 t on both sides. So your actual length for this slender elements is A minus 2 times 1.5 t is 7.652 inches. So, with that being defined, your total loss in area due to local buckling is B minus BE times T. The reason you times 2 because you got 2 pieces of slender stiffened elements here and here. So your total loss of area due to local buckling is 0.6654 inch squared. So the reduced area is equal to the gross area minus the loss in area due to buckling. So your effective A is 2.035 inch squared. So your QA, like I mentioned to you, is AEF divided by A is 0.7537. So your Q factor is QS times QA because you do not have unstiffened elements, so QS is 1. So your Q is equal to 0.7537. So any questions regarding the QA factor calculation so far? Comments?
I have a question on the BE.
Go ahead.
So the design thickness, is it always gonna be
0.93 times the nominal thickness.
only for HSS, right?
Yes. Good question, Lin.
Did they send the coach on my phone, baby?
Yeah, who you have questions?
Yeah. Just what Lynn
Oh,
just
you have to
asked.
turn
Can
it
you
back on,
please
yeah.
answer?
Go ahead.
To save battery. Oh, the phone, the remote died.
0.93 is the design thickness.
Yep, they
So
died.
are they both constant or one of them is variable?
Tell me the code they sent.
You are talking about
868
this one, right?
267.
This design thickness?
Yeah. How did you get the 11.6?
Is 1/8 here times 0.93.
So 0.93 is the constant.
It's a specification constant. It's so-called design thickness. You do a little bit reduction for the nominal thickness. You call design thickness. That's by definition
You
by
out of
code.
school? Your school?
Is that to be conservative?
Yeah, it's conservative. That's correct.
And that's just because it's, you said it's only for HSS, right? If for any
Yes,
other,
yes.
we just,
Only for HSS.
so we would use the entire like actual thickness for any other section, right?
If you, the code wants you to use design thickness instead of use 1/8 for HSS for this equation.
And then, but for other sections other than HSS, we would use the actual thickness, like the entire 1/8, right?
For other section, what do you mean by other section, Andy?
If it's like a W shape or like a, you know,
Oh, W shape, yeah, you use actual. unless the equation require you to use design thickness, then they might have different definition for different shape based on equation.
Okay, excellent.
Actually, she's sleeping. Let her
So it's
sleep.
very nitty gritty. There's a lot of side notes for steel design code. So you need to pay attention to what it means and read it carefully.
This is our chance to prove to
All
them that we're
right.
just like these two. Autonomous,
Any other questions?
super efficient.
So, with that we calculate, you can calculate local buckling strength by plugging into the Q factor to the limits to the separation point between elastic and inelastic global buckling as before, but now you need to put Q factor in here. Then you got 136.2, and then your slenderness ratio is 105.3, less than 136.2. Then you use equation E7-2 equation. But now you need to account for local buckling, so you need to times Q. And then you got 19.76 KSI. Then your nominal strength to account for local buckling is 53.35 kips. So as you can tell, without local buckling effect, your calculation in the beginning is 58.91. So in this case, local buckling will control for this column. So the number, the strength, nominal due to local buckling is 53.35 instead of 58.91. So for LRT, the design strength is VC times PM is 0.9 times PM is 48 kips. If you use ST, its nominal strength 53.35 divided by factor of safety 1.67, which is 32 kips. So this is the simplified approach to estimate the factor, the F in here. You assume F equal to Fy. So like I say, in exams, in homework, you can use this method if you're running out of time. Now, another method you can use is what we call iteration to solve F. So what you can do is you can start to guess the F from any number in the beginning. So in this case, we use FCR. F equal to FCR is 19.76 KSI. This number is coming from the previous steps. We assume F equal to Fy. If you can recall, when F equal to Fy,
You were supposed to call us and you didn't. I'm ordering you to revert to your civilian identities and hand me the source of your powers. We'll have it back
FCR,
in
we got 19.76 KSI.
If your powers
So you can use this as a starting point for F. Then you plug in the F into this equation, repeat the process, okay, and then you calculate FCR. But this number is not equal to what you assumed in the beginning, so which means 19.76 is not a good guess in the beginning. Then you need to repeat a second guess. The second guess you can do is you can use this number as your next trial value. Then you repeat the process. Then you figure out 21.15 KSI also now equal to 21.26. But now it's very close. It's getting closer and closer. So let's do a third trial. Let's use 21.15 KSI for F. You plug into the number here. Then you keep doing the same process. And now these two numbers converge very close. So this is the actual, FCR happening inside the slender stiffened element, the actual stresses. So this is the number we need. So we can plug in this number times AG. Then we got 57.13 kips. So again, this is local buckling control. So this is the iteration method. We got 57 kips for nominal. If you use FY, you got 53 kips. So there are 4 kips differences. This one, you assume F equal to Fy. Alright? But if you do iteration, you got 57.13 kips. Alright, so this will give you more accurate result by doing the iteration method. So any questions regarding the iteration approach? Is similar to the one we just did for assuming F equal to Fy. But now for iteration, you just assume the number for F and then to see if they are converged. This is the calculation based on equation for FCR, and this is the one you assume in the beginning. If they are not matched, continue for the second trial until you find the closed answer for that. So any questions?
Yes, sir.
Go ahead, we.
Show the thread. You went by so fast, though. Can you show each page again for the alternative solution?
Can you speak louder? I cannot hear you very clearly.
How about now, Professor? Is it better?
Yeah, can you speak
Can you
louder?
go to
Go
the
ahead.
next page, please?
Okay, go ahead.
Can you go to the next page, please?
Okay, this page?
Next one, please.
Next, okay.
Any mass gathering would be much too dangerous. As long as Technopirate roams free, we're asking you, dear New Yorkers, dear French guests, to stay safe wherever you are. Meanwhile, we will keep patrolling the city and hold back until we capture him.
And can you show the last one, please?
Okay.
The next.
This is all in your textbook.
Alright, thank you, sir.
Sure. Any other comments, questions for the local buckling?
Yes, sir.
All right.
I have to go. Sorry, Marinette. It's so hard for me to be here. I wouldn't have minded being stuck here a little longer with a friend like you. My father's right. I should have never come to New York.
What is wrong with you, Marinette? Couldn't you say that he was just waiting for you to tell him to stay? What? But he made his choice. What did you expect me to do? It doesn't matter what I expected you to do. Who's Adrian to you? A friend or more than a friend? There will never be a better time to be clear with yourself, Marinette. Do you want him to leave or do you want him to stay?
The next 2 slides, I would like to give you a heads up. So next time when we meet, we'll continue from here. There are 2 powerful tables in the manual when you want to figure out the design compression member strength. they are in part 4 of the manual, table 4-22. And this is based on 13th edition. Page number 4-318 to 4-322. This table is used when the compression member is governed by flexural buckling. This table will give you the value for Vc times FCR for LRT and FCR over omega C for SD as a function of K over R for different value of Fy. The table stops at the recommended upper limit K over R equal to 200. When you use this table, if your member has slender elements, the local buckling strength must be computed, which is Q factor that I just talked about. So this is one of the load column calculation table. Basically, this table calculates this value for you. So basically, that's the equation that we covered in the previous lectures. They just calculate this value for you and put it in the table based on different Fy and K over R. Okay? Then, the next powerful table that you can use is what we call column load table. This is on page 4-10 to 4-317. This table will give you the design strength for different shapes, for VCPN, for LRT, PN over omega C for SD, for effective KL. In this column load table, if you check out the table, your input is KL. It's not KL over R. Because this table, by default, they already consider the R is based on minimum radius of gyration. So what you need to input is just KL. The L is the height of the column, K is the effective length factor. When you use column load table, they give you the loads in kips. If you use this table, 4-22, they give you stresses. So do not confuse. And one thing you got to remember, column load table, good news for you is this. The column load table already consider local buckling effect. So the number you got here is already consider local buckling effect. So no further reduction is needed for column load table. You can make a note. If you see some shape with the footnote C, means they already calculated based on AIC equation, section E7, member with slender elements. So no further reduction is needed. But if you use table 4-22, if you have local buckling, then you need to calculate Q factor to figure out the strength in FCR. Alright, any questions or discussions?
Professor, for the example in finding total loss in area, could you redraw that section again?
Which one?
For the example, to
The
find
total loss?
Yes.
Okay, so you are talking about the previous example?
Yes.
Okay. The total loss. your B is measured, for example, like I said, from here to here, and this is what we call B. All right. So you take this. If there's no local buckling, you can take full B times T as your area. But now due to local buckling, you can only account for example, this is what I call B sub E. Only this is effective. Do you got it, Lin?
Yes. The section you had drawn earlier was round.
Yeah, I just simplify. You need to know this is radius. You want to know this?
The total loss in area. The right under it.
Okay, the first thing we need to do is seize Miraculizer's Miraculous. That way, we'll be able to break the
So
spell.
Professor, I was kind of following along with the example from the book. So, did we ever find the design strength and the allowable strength, or were we just finding Q?
Let me cover with this first with Link. So Link, did you see this?
Yes. And the 1.5 T would be on the side.
On this
right?
center. So you're measuring your B from the center of the radius to the center of the radius. So this is the B.
The arm that leads to the torch platform.
Awesome. But how are we gonna get inside?
And this is 1.5
Who's attacking us?
from here to here.
Teleportation power.
1.5 T.
The statue unnoticed.
So your nominal is 8
He'll never agree to help us.
Besides, how are we gonna find it?
from here
Anywhere in the world.
to here
Curiosity
is 8.
Sparrow, grab a cardboard box and that newspaper and make a wrap.
So your B is 8 minus 3T. This is your B. So your B, if not reducing by local buckling, you can take this number if no local buckling. But now, because you have a local buckling, the B, only B, E is effective to taking the loads. So you are losing B minus BE times T for the area. You got 2 because you got 2 pieces. One in here, another one on the bottom. Got it?
Got it. Thank you.
Mm-hmm. Then what's the other questions?
Yeah, so did we ever solve for the design and allowable strength? Because that's kind of like what the book did. I wasn't sure if we were just...
What's design allowable? Yes. That's in here. Here.
Okay. Okay. Yeah, it looks like they just rounded it up. But yeah, it's pretty much the same. Okay. The BE though that you were talking about before, that was just like that length that you found. That was just calculated, correct?
Yeah.
Okay.
Mm-hmm. Any other questions or discussions? All right.
Sir.
Okay, so if not, then I will stop the class here. I will answer any question if you guys might have. If not, and good luck for your midterm 1 this Wednesday. And I will see you guys next Monday to continue for chapter 4.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you, Chris.
Professor, can I talk to you for a second?
Sure.
Thank you.
Thank you.
Sure, Lee.